I'm very happy to have Aakash Varambhia here to tell us a bit how their internal software stack looks like for doing data science and image analysis.
Thank you. So today I'd like to talk a little bit about how we deliver imaging data science to aid research in Johnson Matthey. So this talk will be focusing more on what we can do, especially with the scientific Python ecosystem that we have. And whenever I come to conferences such as SciPy, I feel a little bit like a kid in a candy store because I come here and I look at all the different types of technologies, tools within our that are here, and basically all the different types of data that we look at, there's some kind of answer that usually tends to help us for our data sets. And we have lots of different types of data here, and they're an absolute pain to deal with. It's not just HDF5s. We have all sorts of proprietary data that we look at, and we need a lot of domain expertise from computer vision, statistical analysis, and machine learning to solve these problems. And we basically throw everything at this that we can to solve for our structures. And to just philosophically think about it as well, it's important not to distract from the science. And what we're trying to do here is design better catalysts. And this is our catalyst design lifecycle. Basically, that diagram is just showing you that we go from some idea, we design a catalyst, we characterize it, we model it, then we go back down through the loop, and there's a bottleneck when it comes to characterization. And given all the tools that are available in Python, what I'm showing today is what a team of 3 data scientists have been able to do with our scientific data science app store that we've made. For those who are not familiar with Johnson Matthey overall, we are a global leader in chemical technologies to help our customers meet sustainability demands. It's a strong brand, over 200 years old. And as a global leader in this space, we recognize all the challenges that we face from global warming, energy shortages, and resource scarcity. And now more than ever, we need tech to answer some of these questions. Our business units are structured around 3 core units, and that is clean air for reducing pollution and vehicle NOx emissions, for example. The other one is hydrogen technologies, so this is automotive industry and alternative energy sources. And the other business unit is catalyst technologies. This looks after our sustainable fuel, synthetic gas, and anything that we have an expertise in catalysis and how can we translate that into industrial processes. There was a talk earlier today in the morning about using Python for early sustainable aviation fuels. And in this space, this is something that we do as well, where we partnered with Virent to launch the first sustainable aviation fuel transatlantic flight with passengers across the pond, essentially from Europe. Now, given those 3 business units, the one thing that they all have in common, and this is at the core and the heart of our business, is the catalyst itself and its design. So for those who are not familiar with what a catalyst is, and I'm hoping people are because it's a materials track, but I just thought I'd put this slide in there. Essentially, at its very base level, all it is, it's a substance that converts molecules from one form to another. So this is in this case, I'm using an example from one of our catalytic converters that goes at the back end of a car, where noxious gases such as carbon monoxide, nitrous oxide, and hydrocarbons get converted into harmless molecules on the other end. Now, where does R&D fit in Johnson Matthey? We're a little bit unique in this sense, so we try and balance both commercial aspects of it. So we want to make catalysts that work better, cheaper, and last a long time. That increases our profit margins, which is great. But also, we want to understand how they work, relate composition and structure to electronic properties, and also find the optimal design. So there are key messages here. There are 2 ways to do this, right? So when you look at this, you have to deal with your structure at what we call the device level. So this is the large scale here, but you also have to deal with your structures at the atomic level. And at the micron scale, or at the device scale, there are 2 components that we usually measure, and that is the gas flow through the channels and the interconnecting pores that we look at. And the other one is the morphology of washcoats, substrate, and support, and the resultant pore structure. At the nanometer and atomic scale, we look at our nanoparticles and the size and shape, and we have pretty sophisticated equipment in the company to look at these materials. And actually, it's one of the most well-kitted out labs in industry for characterizing these materials. So we have X-ray microscopes. Here is a Kinder egg. It's usually the most relatable example to show you this with. We are able to take 3D structures of it. Like, so as you tilt the sample, you take loads of images, and you're able to reconstruct that image, and you're able to get information about your sample that way. We also have what we call a focus ion beam instrument. Here, what you're doing is you're using an ion beam, and you're milling your sample, and then you're taking an image. You're milling, take an image as you go into your sample, and then you get a 3D array that looks like this. In the case of a transmission electron microscope, you fire electrons from the top onto your sample, and then you observe the scattering and also any other signals that are generated secondarily, depending on the interaction your electron has with your sample, and then you get images like this. And these are atomic arrangements that you're seeing of your material. As I said, this is a multi-length scale problem. My slide is not updating for some reason. All right. That's not very good. Yeah, that's the idea. I have a few videos in here. That's probably what's causing the issue, to be honest. Okay. Great. So, in short, there's multiple length scales at play here. And essentially, we have the ability to be able to go from a structure that you're looking at over here to its representation at the X-ray with an X-ray 3D scan to be able to get information at the device level, and then you're able to get extra details with the focus ion beam at the micron level and then the atomic level. And it's nicer to look at this in pictures. Now, the data that we deal with is quite complex, and this is the challenge here. And in our field, when we look at it on a day-to-day basis, the scientists have to deal with too many file systems. They have to deal with all sorts of signals that are coming in. The software is not really open source. It's a lot of proprietary software that we have to deal with. Software is not tailored for our needs as well. We also have a burden where, as a company, as a large company, we deal in a lot of areas. So we have materials that are not very well, nothing is generally standardized in this area. And also we have a need for data scientists because we lack that in the field. So 5 years ago, we decided to look at, so what can we do about this? How can we basically optimize our data analysis pipelines, and can we enable data scientists who are not, can we enable research scientists who are not data scientists be able to do this type of analysis? So we have different types of routines. So in a typical workflow, when you really break it down in a simple form, right? You start with data acquisition, you go down to reconstruction, alignment, segmentation, analysis, and reporting, and there's different tools that allow you to do this. But you can do a lot of this in Python, and at each stage, it's like really important that you're able to actually process the right information with the right tools to get to where to get to meaningful insights. And this is where we've developed a platform that we've built over the last few years, and our company has used Dash as the main platform of choice to do this. And ultimately, the goal is to create a comprehensive ecosystem of tools that supports the entire microscopy characterization of our materials. And essentially here with Dash, what we've done is we've kind of simplified our full stack development process where traditionally you need a data scientist and a back-end developer, a front-end developer. In this case, what we're doing is fast-tracking our software development to be able to get to some kind of what we call minimum viable product to deliver for the organization. We have several apps in this space, and we've built a couple, I'll show an example of one of these. Is just a demo here where basically it's just that easy where you go on a website, you click on one of these images, one of these tiles, you get to your app, you're able to upload images, apply filters, apply thresholds, and then get your particle size and your graph, for example, and get your report end to end. The other thing that this allows you to do, especially if you have a web interface or a web framework, is that you can basically save a lot of this data for future machine learning training because we still rely a lot on like threshold or classical segmentation methods or machine learning based segmentations, but this allows us to get that leap forward in deep learning as well, where we're collecting this data. So you're actually leveraging a lot of users to actually, like, you're kind of coercing them in a nice way by giving them a reward at the end of the day by getting them to work on a certain material. So I'm going to walk through now a typical pipeline for, like, I said there are two types of things. So like, how do we actually, so if we have an app store like this, how do we actually go to design better materials, right? Because that's the end goal of what we're trying to do here. And I'll start with the micron scale. As I said, it's the gas flow through the channels that matters. So right off the bat, talking about the pipeline from the top here, data acquisition, reconstruction, alignment, as I showed earlier, segmentation, analysis, and reporting, is we make heavy use of scikit image where we can. Wherever possible, we also try and parallelize our code as we, you can imagine when you make graphical user interfaces, you kind of want your code to be a bit fast because, okay, in a Jupyter notebook, in a cell, you might hit Shift Enter and you can wait, and that's okay. But when you have a lot of users who are not used to coding or they just want things to be really smooth, it's really, really important that you actually have made your code performant in that area. I would also like to highlight the role of Xarray in managing our multi-dimensional data sets because inherently our data is multi-dimensional, multi-lens scale. We're dealing with different types of like one of the things here, here's a very good example that we've not really solved very well. It's, say we have an XRM scan here. We can scan the same region over here at a much, much higher detail. How do we incorporate these two data sets together? Like the GeoPython field has solved this by using layers to solve this type of problem, but here it's inherently a 3D problem. How do we actually go about visualizing a data set like that? Another thing, actually, when we deal with images, we get a lot of artifacts in them as well. So these are artifacts that arise from ion beam damage and sample charging. You may see these as like these artifacts here that are like these vertical lines in your image. So I'd like to highlight one of these libraries here from Jonathan Schwartz here for removing these type of artifacts. So basically, when you have an artifact like this, it appears, when you take a Fourier transform of it in your frequency space, it appears in the perpendicular direction. When you put a mask on top of it and then you do an inverse Fourier transform, you get rid of it, but then you're missing information from this wedge because you masked it. You can use this compressed sensing to actually get a little bit of a better result on there. Now, we really like this algorithm, but one of the issues a lot of times is like, while the approach is effective, it's quite slow, and compressed sensing relies on an iterative process. So we try and also use QPy a lot to actually speed up a lot of our code because you're dealing with images that are quite high in resolution. They may have 3,000 to 4,000 images in a stack. You want to be able to process it much, much faster. And in some cases, you can actually just use QPy to just plug and play in your sequence. Similarly, actually, when you're doing data alignment, another library I'd like to recommend here. So like we have a 3-step process. So sometimes we do template matching to align our images. So when you take these tomograms and scans, you sometimes have drift, you have other issues, you may have instabilities in your samples, you want to correct for these. And we have different processes to do that, from template matching, rigid alignment, to optical flow methods. And we've recently become quite a big fan of using QSIM. It's basically, as far as I'm concerned, in my eyes, a GPU drop-in replacement for scikit image overall, and it's very, very performant and very nice to offload a lot of that work onto the GPU when you're doing your processing. In a lot of cases, you'll see fast improvements of code between 200 to 400 times when you're doing this type of work. And then you come down to a pre-processing step before you do your segmentation. Here we usually bundle a lot of the things that we do with Dask so that we can actually go through a lot of their images and process them much, much faster. Eventually, why do we do all of this? As I said, it's the philosophical part, which is the science of it, right? At the end of it, and after all of that, you get to the step where you're finally able to actually get some of these results. So the things we're interested in are pore sizes. How can we actually design these? How can we actually design our pore connectivity to be better? How can we design our pore networks to be better? And then the material coverage and uniformity of our samples. And here I'd like to highlight PoreSpy as one of these very, very good libraries in our workflows for doing this. So that's a lot of tech that I've shown very quickly while I also crashed, so trying to catch up on time, is that we encapsulate all of this complexity inside an app that looks deceptively simple overall. It's a few buttons that people press to actually get the results. And see, in a company, what's important is the end-to-end process of being able to then generate a report at the end of it. So that's what you're getting on the right here as well. Another thing I'd like to highlight here as well is that as we've been going down this journey overall, you know, in a lot of traditional companies overall, it's quite closed space overall. A lot of the code that you're developing stays in-house and that sort of thing. But as we've been developing these apps and, you know, people realizing the importance of these things, we also have a little bit of funding where it comes to open source projects and that type of work. So here's one of the libraries that we have sponsored some of the features for, such as IPy volume, and we're now working with Solara to actually get some of these combined together to form into plugins. So if you have any ideas or if you think you have libraries that can help us, please do reach out to us and we can see if we can fund those. And you know, as I said earlier, it's all about improving that poor network structure. So what we do is we use these as inputs for real simulations and design better pore structures. So here are some synthetically generated structures that we've made. Now, the thing is, this is just one part of the story, right? Because like once you've actually generated your best pore structure, how can you actually, like, you know, it's all well and good that your gas is reaching to the right places, but the other thing that you have to worry about is your nanoparticles, because that's where the real chemistry happens. And this is where what I call scanning transmission electron microscopy is king in this area, and this is like the level of detail that you get with this technique is quite impressive, right? Because this actually gives you the fundamental understanding of your materials. So, you know, you can go from your sample over here to get an overview of it. You can see the distribution of your nanoparticles. They're usually in these powders, and this is what goes inside your pores, right? So then you're able to get atomic structure information. And essentially what we want to do is from those images and those snapshots, come up with 3D models and then pass those into DFT for modeling. And we have deep expertise in this area. I'm not going to go too much into detail about this, but we have a method where we can actually treat the electron microscope as a particle scattering experiment and treat the intensity that you're seeing within the image observed via the scattering that you're seeing at the detector level to be able to express this intensity in terms of the fraction of the scattering that you've observed as your electron is interacting with the sample. And essentially, once you have that expressed in that manner, you can then do what we call atom counting on it, where you take your picture, you apply 2D Gaussians to fit atomic positions on there, and then count the number of atoms that are coming, like what is the number of atoms per each column that you're observing over here. And a lot of the code in this space, I would say, is was in MATLAB as it was developed at the time. But my predecessor in this project, when she was in the group as a PhD student, developed and pioneered a lot of these atom counting techniques, and these are now available in these libraries for AtomMap and HyperSpy over here. These are freely available, and there's actually a talk on HyperSpy that is happening. I was actually very, very pleased to see this, because it's like the electron microscopy. Oh, okay, so it's you. That's good, because it's like the electron microscopists have made it to like sci-fi, which is great, because you know it's one of those really, really useful toolboxes in our area that allows us to do this type of work, and this is one of the things that has come out of it. And what it allows us to do is it allows us to actually, you know, those automated routines and processes allow to fingerprint our nanoparticles. So what I'm showing here is this is no longer just a pretty picture. What you're seeing here is a picture with the number of atoms as an estimate of what this is. So these are pure platinum nanoparticles in this case. And when you look at how they match with theory, so this line here is theory, and our particles sit relatively well in agreement with it. And with that, you can like back reconstruct, or you can go inverse, right? You can do a structural inversion of this and get 3D structures out. And you can compare these to theory, essentially, and then you can look at how the bulk-like structure looks like, how the 111 edges look like 110, and with this coordination number analysis, you can now link that to oxygen binding energies, because that's one of the things that you want your catalyst to be able to perform with. And this is where the true science comes in, because now all of a sudden what you have is a very, very powerful descriptor that's telling you, okay, this is your theoretical line here, for example. This is your experimentally observed line. The closest these two are, because experiment's never going to be perfect or your observation's never going to be perfect, but the closest that they are is where the right or design or where the right nanoparticle design needs to be, or that's where you can target the chemist to then go and work on to create particles of that type of shape for a specific reaction. This is also very, very powerful because not only can you interrogate these models, you can you could do other things, right? You could do simulated annealing experiments. You may also be able to perform what if scenarios of what is going on with your system, or I don't know, you may try different molecules and see how they stick on top of these facets, that type of work. And tweaking these parameters actually moves us closer to better particle design overall. And our ambition overall, now, I would say after everything that we put in place, okay, so we've kind of solved a lot of the problems for the micron level. The next step here is actually, can we do this live? And this is the pipeline that we're trying to build in the future. And then can we do this with a web interface? So you can imagine a bit like Twitch TV, but for electron microscopes, where if we can actually, using deep learning for navigation and whatnot, using all of our structure inversion methods. So, this was about 13 nanoparticles is what we did in this paper, and that took about 3-4 years. But the future of this sort of stuff is live, it's real time. And there's a talk that's happening right after mine, and this is where I'm rushing off to in a bit, because Diamond Light Source is trying to do this with something called tychography. And we've just started this in electron microscopy overall as method, right? And one of these particles is about 0.5 terabyte of data that you are looking at to analyze with these new techniques. And we would like to be able to see they claim they can do it live, so let's actually go and see what they're trying to do with it. And to actually support this vision in this space in the UK, I've applied for a grant in this area, and specifically one of the clauses in there is actually supporting there are niche libraries, that open source libraries, that if they could help us, that'd be really, really good. So if you have any ideas, please come talk to us in this space. And that sort of brings me towards the end of my talk. And actually, if you find anything interesting, so this is a bit of a self-advert here that I've put in. Please check out our careers page for Johnson Matthey. We have lots of vacancies in this areas for scientific R&D. There's a graduate program, apprenticeship, and also if you're interested, talk to us. And also I'd like to acknowledge my team and also my previous research group in Oxford, where a lot of these techniques were developed. Thank you.
Thank you so much for this exciting presentation. Are there any questions?
So first, England 2, Netherlands 1, England and Spain next round. The question, sorry, Mr. Chairman. So the question is, if you're integrating all of these tools, how much of your team's effort is going into just gluing them together, getting them to talk to each other?
I first have to repeat the question for the online audience. So the question is, since you're integrating all of these tools, how much of the work goes into just gluing them together?
So it depends on the maturity level of these libraries. So a long time ago, actually, I'll start with HyperSpy as an example over there. There was a lot of so back in the day, they didn't have integration with Dask, for example. They didn't have integration with Number. You had to do this yourself. That was 5 years ago. That's where we started. But now these come out of the box. That these are already in there. So I think it's a question if you'd asked me 5 years ago, I'd have said a lot of time. But now, not necessarily. It just depends on the challenge. Yeah.
Please go ahead. Yeah.
Can you comment on your team? Because you have a core set of developers and other researchers contributing. Are they also doing the development, or is it just the core developers?
So the question is, where does the development happen? Does it happen just in your core team, or do other researchers also contribute code, for example?
So mostly it is, I would say, so what we're doing here is we're using a platform to as Greg put it, like to glue things together. So a lot of that development is writing software code between 3 people full time doing that. But a lot of the development is the academic sponsorships that we have within Johnson Matthey. So we have, for some of these projects, about 6 generations of PhD students who have worked on it. And they are the core people who work on it. So it's years of development. And that's usually through Oxford, but then it's also the microscopy community overall. And then there's a big Python community there as well that we leverage.
Please.
You mentioned a couple of web-based apps, but do you provide any non-web-based apps, things that you can install locally and work with your own servers or own infrastructure?
So the question is, you mentioned a web platform here. Do you also provide tools that people install locally? Is that correct?
Well, not at the moment, and the main reason is because it's a bit like how our remit works in an industrial setting. So we're in a chemicals company where 90% of the chemists do not code overall. And how do you deliver tools? We have so much cool things over here. How do you actually deliver them? And that's always been a bit of our calling in many ways. And actually, you find this a lot in so. We speak a lot to Diamond Light Source, which is one of the UK's national labs, and that's where we collaborate with them if we were to release something in that sense for users. And actually, that's also one of the problems they face as well. Is a lot of these national labs, they have people who come in and they gather a lot of data and then they go off, and there's very little aftercare on how it works. What we're trying to provide here is interfaces where it's easier for people to be able to do their analysis very quickly, because that's what they care about. The chemists just care about the results too, and because they want to move on to the next experiment.
I briefly take the privilege to ask a question myself then. So these Python dashboarding frameworks, they're great to get started, but then often once you start getting into more complex apps, things get complicated. So I was wondering whether you could talk a little bit about that and how you test them, how you monitor them, and so on.
Yeah. So I think it depends on like the complexity or how it is. The way we tend to work on them is sort of like, you use your standard test-driven development, and that's how you do it. This is where it gets a bit, I guess, I'm going to mark it a little bit, or just say on the side that we prefer Plotly overall in this area, because it's given us it's been enough on the underlying complexity there, or how modular, or how it's designed with its callbacks. We've noticed it's worked quite well for everything we've thrown at it so far, and that's what we've usually relied on. It's just that the way the architecture is designed is what has made it. Yeah. Okay.
I think he was first then you.
How much time would you guys say you spend on maintenance for these apps? So you guys have a few now. If you add 2 or 3 more, are you worried about needing to scale out your team, or do you have another team that kind of deals with that?
The question is, how much time do you spend on maintenance of these applications?
So quite a bit. But the way we actually designed this, there is a bigger initiative here. There's a layered answer to your question, and that is like what we try and do, or the way we operate, is that there may be a certain chemist or a certain research scientist who is interested in a certain app, and a lot of times it's a part of an upskilling process in the company where you're working with someone to actually create a tool for them, and then as they get upskilled along with it, they then are the owner of it, and that is a holistic way of scaling up. So there are some apps we maintain, there are some apps other people in the team maintain, like in their respective team outside of our core team.
You showed in the one example that the user would upload their data, but you've also mentioned that some of the data sets are like terabyte scale. So how do these dashboards like that, how do you handle the data management that goes on the back end? That a user accesses their data or whatnot? Because I'm in a sort of similar space with imaging in biosciences, and as the data sets are now terabyte scale, it's really annoying. You can't really just shuffle it around on a USB stick.
The question is, you showed some apps where users can upload their own data, but then you also mentioned terabyte scale datasets. How does that work?
I don't have a proper answer to it, to be honest, either. We use a combination of ways. So we don't have just, I can't just go and tell you, I don't know, use Kubernetes or use, I don't know, this VM or use this other way of doing things. We have multiple approaches. So we use platform as services, we use VMs, we actually have servers that sit next to an instrument as well as one of the options. It really depends on what the problem is. And in the case of the really large data sets, it's literally buying server racks that are sitting next to them. In some cases, it's leveraging the HPC compute in a national facility as the other way. So we try and not, we don't have a one size fits all, to be honest. It really depends on the problem. Yeah.
Last question.
So, have you ever been in a case where one of the open source packages you were depending on was orphaned? The maintainers walked away. You know the scenario. Has that ever happened to you? How did you deal with it?
The question is, has there ever been a case where an open source package that you were relying on was abandoned?
That does happen. Yes, it's happened before. Yeah. In many cases, actually, this is the advantage that you end up with in a company sometimes is, or when you come down to SciPy or wherever, is if there is enough monetary justification, it all comes down to the economics of it, right? How much? So in a business, it's like, how much does the business value this, and how much does the business need this? And then depending on that equation or how it's balanced, they're willing to throw money at it if that's something that happens. So then in that situation, you then hire a contractor or someone else to look after it, a very specific solution for you. Yeah.
Well, with this, I'd like to thank our speaker again for a great talk.